Hello everyone, and thank you for joining this webinar. In this part of the webinar, we will focus on how nature-based solutions help reduce urban heat and how they support renewable energy communities in Mediterranean cities. This webinar is part of the EnerCmed project. Its main aim is to promote the energy transition in port hinterlands through the development of renewable energy communities that are integrated with nature-based solutions. The reason behind this project is very clear. We want to reduce energy poverty in the most marginalized urban areas, while at the same time using nature-based solutions to mitigate the urban heat island effect. The project is being implemented in 5 residential areas of port cities across the Mediterranean, specifically in Spain, Croatia, Greece, and Italy. Finally, the main actors involved are Mediterranean municipalities, urban authorities, and local stakeholders, who play a key role in implementation and decision-making. The goal of this webinar is simple. I will explain what nature-based solutions are and how they help reduce urban heat island effects. I will focus on Mediterranean urban areas and show how these solutions are connected to renewable energy communities. Finally, I will explain why this approach is important for building climate resilience. Cities are usually warmer than their surrounding areas. This is known as the urban heat island effect. It happens because cities change the natural energy balance. Vegetation is removed, and dark surfaces like roads and buildings absorb and store heat. This heat is then released back into the air, especially during the night. So why does this matter for renewable energy communities? Higher temperatures lead to higher energy demand, mainly for cooling in homes and buildings. This puts additional pressure on energy systems, including renewable energy communities, especially during heat waves. The urban heat island effect happens mainly because of how cities are built. Buildings, roads, and pavements are very dense, and they trap heat. Most urban surfaces are also dark, so they absorb and store a lot of solar energy. At the same time, cities have much less vegetation than natural areas. Because of this, there is less cooling from evapotranspiration. In addition, energy use in cities is high, coming from cars, air conditioning, and other human activities. All this extra heat is stored during the day and then released back into the air, especially at night. The urban heat island effect does not occur at just one level. Urban warming happens at different layers of a city, and each layer behaves differently and stores heat in its own way. First, we have the subsurface urban heat island. This refers to heat stored below the ground, under streets and buildings. Then, there is the surface urban heat island, which is related to roads, roofs, and pavements that heat up strongly during the day. Above this, we have the canopy layer urban heat island. This is the air layer between buildings, where people actually live and move. Finally, there is the boundary layer urban heat island. This affects the higher urban atmosphere and influences how heat is transported over the city. All these layers interact with each other and together form the overall urban heat island effect. The urban heat island effect has many real impacts on cities. First, it strongly affects human health. High temperatures increase heat stress and reduce thermal comfort. Hot nights can also disturb sleep and limit recovery. Urban heat also increases energy demand. People use more air conditioning, especially during heat waves. This leads to higher electricity peaks and puts stress on the energy system. Air quality is another important issue. High temperatures enhance smog formation and increase ozone production. Finally, urban ecosystems are affected. Plants experience heat stress, their growth cycles can change, and biodiversity can be reduced. Overall, the urban heat island is not just a temperature issue. It is a combined environmental, social, and energy problem. Nature-based solutions use natural elements, such as vegetation and water, to address environmental challenges in cities. They are categorized based on the main natural process they use, such as vegetation, urban form, or water. In general, we can group nature-based solutions into 3 main categories. These are vegetation-based solutions, urban design solutions, and water-based solutions. In the next slides, I will briefly explain how each of these categories helps reduce the urban heat island effect. Let's start with vegetation-based solutions, which are one of the most effective ways to cool cities. Vegetation-based solutions use plants and green infrastructure to reduce urban temperatures. This includes elements such as trees, green roofs, green walls, and urban parks. Trees provide shade and cool the air through evapotranspiration, which is the process where plants release moisture into the air. Green roofs and parks also help lower surface temperatures and reduce heat stored in the city. Typical examples of vegetation-based solutions include green roofs and green walls on buildings, urban forests and street trees, parks and green corridors within the city. Vegetation-based solutions provide many benefits at the same time, especially for reducing urban heat. First, they help with thermal regulation. Trees and plants create shade and cool the air through evapotranspiration, reducing both air and surface temperatures. As a result, thermal comfort is improved. Streets, parks, and public spaces become cooler and more comfortable, especially for pedestrians during hot days. Vegetation also improves air quality by absorbing pollutants and reducing ozone formation, which is common during heat waves. Another important benefit is stormwater regulation. Green areas allow water to infiltrate into the ground, reducing surface runoff and flooding risk. Finally, vegetation-based solutions provide ecosystem and social benefits, supporting biodiversity, improving well-being, and making cities more pleasant places to live. This slide explains how vegetation-based solutions reduce heat in practice. Trees reduce thermal stress, mainly through two key processes: shading and evapotranspiration. The tree canopy blocks direct solar radiation, so less sunlight reaches the ground and surrounding surfaces. At the same time, trees release moisture into the air through evapotranspiration. This process removes heat from the environment and helps lower air temperatures. As a result, areas with trees experience lower surface temperatures and improved thermal comfort. This is especially important in streets and urban canyons, where people are exposed to high heat during the hottest hours of the day. The example shown on the right comes from an investigation study using computational fluid dynamics. The study examines how even single trees placed inside a typical dense Mediterranean urban canyon can significantly improve thermal comfort. The simulations are based on the historic city center of Nicosia and focus on thermal comfort at pedestrian height. The graph compares conditions with and without trees, and we can clearly see that the presence of trees leads to much lower thermal stress. This highlights how targeted, small-scale vegetation interventions can have a strong cooling impact in dense urban areas. Next, we move to urban design solutions. These focus on how buildings, streets, and materials are designed and arranged in the city. The main idea is to reduce heat absorption and improve airflow in urban areas. Examples include the use of cool or reflective pavements, shading structures like pergolas or awnings, and street layouts that allow natural ventilation. Building orientation also plays an important role, as it can reduce direct solar exposure and limit heat gain. Compared to vegetation-based solutions, these interventions often involve changes to the built environment. First, they reduce heat absorption. High albedo and cool materials reflect more sunlight, so surfaces like streets and roofs remain cooler. They also improve thermal comfort. Shading elements, better street orientation, and ventilation make outdoor spaces more comfortable for pedestrians, especially during hot summer days. Another key benefit is lower energy demand. Cooler buildings need less air conditioning, which reduces cooling demand and energy use. Urban design solutions also improve the local microclimate. Better airflow helps prevent heat from being trapped between buildings and removes warm air more efficiently. Finally, these solutions increase urban resilience, helping cities cope better with heat waves and future climate extremes. To understand how these solutions work, we need to look at how urban surfaces interact with solar radiation. When sunlight reaches a surface, it is divided into reflection, absorption, and transmission. Dark materials, such as asphalt or dark roofs, absorb a lot of radiation and store heat. This stored heat is released slowly during the night, which is why cities often remain warm after sunset and the urban heat island persists. In contrast, reflective materials absorb less heat and stay cooler. Shading reduces direct solar radiation, and natural ventilation helps remove warm air from urban spaces. By limiting heat storage and enhancing heat removal, urban design solutions play a key role in reducing urban temperatures and improving thermal comfort. Finally, we come to water-based solutions. These solutions use water and moisture to cool the urban environment. They include elements such as urban wetlands, rain gardens, fountains, ponds, and permeable pavements. All these features help cool the air through evaporation while also managing rainwater. In Mediterranean cities, where heat and intense rainfall often coexist, water-based solutions are especially important. Water-based solutions provide several key benefits at the same time. The main benefit is evaporative cooling. Open water surfaces and moist areas remove heat from the environment through evaporation, lowering air and surface temperatures. They also help reduce heat storage. When surfaces remain moist, they absorb and store less heat during the day. As a result, thermal comfort improves. Areas near water features feel cooler and more comfortable, especially during heat waves. Another major benefit is stormwater regulation. Rain gardens, wetlands, and retention systems store, infiltrate, and reuse water, reducing runoff and flood risk. Overall, water-based solutions combine cooling, comfort, and flood control in a single intervention. This slide shows how water changes the way heat behaves in urban areas. When energy reaches urban surfaces, it is divided into sensible heat and latent heat. Latent heat is the energy used for evaporation, which is a cooling process. In dense cities, many surfaces are dry and sealed. This limits evaporation, so most energy becomes sensible heat, increasing surface temperatures and heat storage. When water bodies or moist surfaces are present, more energy is used for evaporation. This removes heat from the environment and lowers both air and surface temperatures. Stormwater retention, infiltration, and water reuse help keep surfaces moist for longer periods. Nature-based solutions are not only environmental measures. They also directly support the performance and resilience of renewable energy communities. Urban heat, flooding, and other climate extremes increase energy demand and place strong pressure on energy systems. During heat waves, cooling needs rise sharply, leading to high electricity peaks in renewable energy communities. High temperatures also reduce the efficiency of renewable energy technologies, especially photovoltaic systems. When temperatures are very high, PV panels produce less electricity, exactly at the time when demand is highest. At the same time, climate risks threaten infrastructure, social cohesion, and the long-term viability of renewable energy communities. Extreme heat and flooding can damage systems and reduce public acceptance and participation. By reducing urban heat and improving local climate conditions, nature-based solutions help stabilize energy demand, improve renewable energy performance, and strengthen the overall sustainability of renewable energy communities. Now that we have seen why nature-based solutions are important, let's look at how they can actually be implemented in practice. Within the EnerCmed project, we propose a clear and iterative NBS project cycle. This helps ensure that interventions are well-structured, inclusive, and effective. The cycle starts with stakeholder engagement. From the very beginning, we work closely with local communities, municipalities, policymakers, and technical experts. The next step is assessment. Here, we identify key challenges such as urban heat island hotspots, energy poverty, and vulnerabilities in the existing infrastructure. Based on this understanding, we move to project planning. Clear objectives are set, and the most suitable nature-based solutions are selected for each local context. This is followed by action planning and implementation, where the solutions are designed in detail and applied on the ground. Finally, monitoring and evaluation allow us to check whether the interventions are delivering the expected benefits and to adjust them if needed. Importantly, this process is not linear. It is adaptive and iterative, supporting learning, improvement, and long-term impact. In order to support replicable cities, we developed a portfolio of small-scale nature-based solutions. The goal was to provide practical and transferable solutions that cities can easily adopt. Instead of focusing on large and complex interventions, we focused on small-scale measures that can be implemented step by step. This portfolio includes vegetation-based, water-based, and urban design solutions. For each solution, we clearly describe the type of intervention, the problem it addresses, the key stakeholders involved, and the main challenges for implementation. The portfolio is designed to help cities understand what works, where it works, and under which conditions. It also supports decision-makers in selecting solutions that match their local climate, urban form, and social context. By doing this, we make it easier for other Mediterranean cities to replicate and adapt these nature-based solutions, strengthening climate resilience and reducing urban heat island effects. To further support replicable cities, we developed clear terms of reference for renewable energy community development. These terms of reference provide a structured framework for integrating nature-based solutions into REC planning and implementation. The idea is to guide cities step by step from the early diagnosis stage to implementation and monitoring. We created a checklist that helps local authorities and planners assess urban heat stress, land use, vegetation cover, and existing infrastructure at the neighborhood level. This ensures that nature-based solutions are considered from the very beginning of REC design. The framework also includes stakeholder engagement, feasibility analysis, and impact evaluation. This helps cities address technical, environmental, and social aspects in an integrated way. By using this methodological approach, cities can systematically include nature-based solutions in renewable energy communities, especially in vulnerable and marginalized neighborhoods. Overall, this makes REC development more robust, transparent, and easier to replicate across different Mediterranean urban contexts. Now let's see how this works in practice by looking at how different nature-based solutions were applied in the EnerCmed pilot projects, starting with the Valencia pilot. This slide shows an example of how the nature-based solutions project cycle was applied in the Valencia pilot. We started by engaging stakeholders. We worked closely with the school board, teachers, students, and families. Through participatory sessions, we identified local needs and priorities. Next, we carried out an assessment. We identified areas with extreme heat exposure in the school playground. Temperature measurements confirmed that unshaded areas experienced very high heat stress. Based on this, we moved to project planning. We evaluated the use of a bioclimatic pergola as a nature-based solution and explored how it could be combined with on-site photovoltaic energy production. Then, in the action planning stage, we designed an intervention that combines shading, evaporative cooling, and natural ventilation. We also defined clear performance goals, mainly focused on improving thermal comfort. The solution was then implemented by installing the bioclimatic pergola in the most heat-exposed area of the playground. Renewable energy was used to support assisted evaporative cooling. Finally, we monitored and evaluated the results. Air temperature was monitored, and simulation tools were used to quantify the cooling benefits. This project cycle provides a clear and replicable pathway for implementing nature-based solutions in other cities. This slide focuses on the results of the Valencia pilot. On the right, the maps show the change in shading conditions at 11 o'clock, comparing the situation before and after the installation of the bioclimatic pergola. With the pergola, shaded areas in the playground clearly increase during the critical hours. The graph below shows the impact on thermal comfort using the UTCI index. During peak hours, UTCI values drop from around 42 degrees Celsius to about 34 to 36 degrees Celsius. This reduction is important because it shifts conditions from very strong or extreme heat stress to moderate heat stress. In practice, this means the space becomes usable and safer during hot periods. So, this slide demonstrates that the intervention delivers clear, measurable improvements in thermal comfort, exactly where and when they are needed most. This slide presents the PULA pilot, which focuses on improving thermal comfort at a public bus stop. The intervention involved greening the bus shelter by installing 6 planters with climbing plants. The idea was to introduce vegetation in a very limited urban space, where traditional greening is difficult. The planting system was carefully designed with drainage and root barrier layers. This ensures proper plant growth while protecting the structure and surrounding infrastructure. The main goal of this intervention was to improve thermal comfort for public transport users, especially during hot summer conditions. At the same time, it helps reduce local urban heat island effects. On the right, the simulations show how vegetation lowers surface temperatures around the bus shelter. The results highlight cooler surfaces and improved microclimatic conditions compared to the non-green scenario. This pilot demonstrates that small-scale, low-cost nature-based solutions can provide meaningful cooling benefits in dense urban areas and can be easily replicated in other cities. This slide presents the PATRA pilot implemented at the 6th Technical Professional School. In this case, the intervention focused on the school building itself. A 120 square meter green roof was installed on part of the building's terrace, with targeted planning to ensure effective cooling and long-term performance. In addition, green walls were installed, covering about 20 square meters. These vertical greenery systems help cool the building facade and improve the local microclimate around the school. The combination of green roofs and green walls reduces heat absorption by the building, lowers surface temperatures, and improves indoor and outdoor thermal comfort. Thank you for taking part in this EnerCmed webinar. For additional resources, detailed methodologies, and pilot examples, you are invited to visit the EnerCmed Knowledge Sharing platform using the QR code provided.
Hello everyone, my name is Helena Stenberga and I represent IRENA, the Istrian Regional Energy Agency, and today I will present how coupling PV systems with the NBS solutions can provide an integrated response to 2 interconnected challenges in the Mediterranean area. So the throw challenges are energy poverty and the urban heat island effect. So through the EnerCmed pilots, we explored how technical design, regulatory frameworks, social dimensions must be addressed together in order to create scalable and inclusive urban energy solutions. So it's a known fact that Mediterranean cities are experiencing rising temperatures that are even more intensified by the urban heat island effect. So built surfaces such as asphalt and concrete absorb and re-emit heat, making urban areas significantly warmer than the surrounding vegetated greener zones. This then directly increases the cooling demand in the area and consequently energy power and energy bills. So the most affected by these effects are vulnerable groups, which include elderly people, children, low-income households, and persons with disabilities, and everyone else who are less able to adapt to rising energy costs and extreme heats. So the EnerCmed approach combines the NBS solutions and PV systems. This presentation focuses more on the PV systems. So just to mention that NBS solutions reduce surface temperatures that improve shading and microclimate in the area, and they also mean lower cooling demand. PV systems, in contrast, provide local renewable electricity, which reduces dependence on external energy sources and lowering costs. When combined, these two not only reduce emissions, but they also improve thermal comfort for people and resilience in public spaces. So renewable energy communities here act as an enabling mechanism that allow energy sharing on the local level and support socially inclusive energy transition for all the mentioned vulnerable groups or those who live in, for example, heritage areas and are unable to apply the energy efficiency measures. So the pilot sites within the EnerCmed project are Genoa, Pula, Novigrad, Patras, and Valencia. So the pilot sites were selected using a combination of technical. So the pilot sites within the EnerCmed project are in Genoa, Pula, Novigrad, Patras, and Valencia. And these pilot sites were selected using a combination of technical, social, regulatory, spatial, and microclimate criteria. The focus was on public buildings because they do provide a strong foundation for replication and scaling, which is one of the EnerCmed project focuses. So technical feasibility included roof availability, structural conditions, and grid connection capacity, while the social criteria, of course, considered the presence of vulnerable groups and the building's public function. Spatial aspects then addressed alignment with the urban planning regulations of the area and location within the dense urban fabric. Regulatory compliance with energy sharing rules is crucial, as well as grid constraints is also essential in the case of energy communities by the definition. And finally, microclimate factors such as exposure to high surface temperatures and lack of shading were analyzed among all pilots to determine the places that need some form of NBS solutions. So to get these certain results, especially focused on energy demand, we focused our analytical framework based on the highest available resolution data, which was to start 15-minute intervals of the building's demand. So this level allowed us to move beyond the annual averages and understand the real operational patterns. So we first conducted a baseline consumption assessment from each pilot building, identifying seasonal and daily variations and demand intensity, and in parallel, a PV production on site was modeled using site-specific parameters to ensure as realistic as possible generation of the demand profiles. So the recommended sizing of the PV plant is based on the general demand profile, not only peak loads, because oversizing the PV plant could potentially lead to grid constraints. So each building type then revealed distinct consumption profiles, which in general becomes a key input for design decisions, and the core of the methodology was actually focused on overlapping between the PV production and electricity demand. And these numbers should be as close as possible in general, but it is impossible to aim for the perfect overlap, which always then results in some kind of surplus energy, which could be used for sharing based on the demand of other buildings in the energy community. What you see on this slide is stimulated 15-minute electricity consumption for the school in our Patras pilot over 1 full year. So as you can see, the demand profile is typical for one school with peaks in winter months when school is operational and extremely low demand during the summer, which is not a problem in generally in Patras since the solar irradiation is above the European average all year round. So they cover a bit more than the average European country in the winter. So by introducing the seasonal variability and probabilistic weather factors such as cloud factors and sunrise and sunset time stamps for each month, we ensured the model fits real location scenarios for PV production and for modeling the demand side as well. So monthly totals were fixed as reference values, and this approach then ensures internal consistency while making temporal realism at the 15-minute resolution. This graph on this slide shows the overlap between the consumption in blue and the PV production in the orange color at the 15-minute resolution during all year. So as we can see in the winter months, consumption exceeds production, meaning strong grid dependency. But in the summer, the PV production often surpasses demand, which creates a lot of surplus energy. And then this seasonal mismatch actually highlights the need for the energy sharing. So the analysis revealed strong variation in load profiles across different building types. The level of alignment between PV production and demand differs significantly depending on the building function. And as a result, self-consumption rates varied and surplus energy appears in specific seasonal periods. And this confirmed that no standardized solution fits all pilot sites. However, standardized analytical approach that was used within the EnerCmed framework can be applied consistently on every Mediterranean or other places. On the following slides, on the following few slides, we present the technical configurations developed for some of the pilot cities. Each pilot site has self-consumption above 50%, except the Pula pilot, which has about 37% self-consumption a year due to strong variable daytime demand. But in contrast, healthcare facilities had self-consumption up to 94% due to their stable 24-hour consumption profiles. So on the left, you can see our pilot of Patras with the technical design and on-site implementation, while on the right you can see the technical solution for our Novigrad pilot. On this slide, on the left, you can see our Italy pilot, the Ferrero School, and on the right, you can see the technical design for the Children's Creative Center in the Creations Pula pilot. Here's the final technical design within the EnerCmed project, which is in the second pilot within Italy, which is the Volta School, which is in the same energy community as the previously mentioned the Ferrero School. The implementation in general between pilots varied also due to the ownership structures, national regulatory frameworks, grid connection procedures, and building-specific technical constraints. We have one example in the Novigrad pilot, which was one of the most challenging within the EnerCmed project. So in Novigrad, the initial plan was to install about 50 kilowatts, but the demand analysis then indicated a need closer to about 150 kilowatts. However, in Croatia, systems above 100 kilowatts require a connection to the transformer station, which then increases grid connection complexity and cost as well. Additionally, during the implementation, poor roof condition required parallel reconstruction works along with full construction design documentation, fire safety study, and formal approval from the public authorities that own the building. Surplus energy cannot be managed without structured sharing mechanisms. So renewable energy communities therefore require both regulatory and organizational readiness. Early coordination with grid operators and public authorities is essential, and most importantly, grid absorption capacity and infrastructure condition act as enabling preconditions for energy sharing. Renewable energy community development not only depends on the technical design itself, but also on governance and network readiness in the area. On the photo on the right, we can see the case of energy sharing within the Italian energy community. So in the Italian case, surplus energy is virtually shared within the renewable energy community through a regulated allocation mechanism calculated at one transformer substation level. So financial incentives are then distributed among members according to predefined sharing criteria, which is usually defined in the community's individual statute. So to support the replication beyond the pilot sites within the EnerCmed project, the EnerCmed provides a few structured tools. One of them is the Atlas, which essentially offers a strategic overview of coupled energy communities and NBS models, while the national handbooks then translate these concepts into pilot countries' specific implementation guidance. Self-assessment tools are also being developed to help cities or municipalities or even households in the future to evaluate their readiness to enter the energy community, ensuring transferability across the Mediterranean context. So just a short conclusion at the end. So coupling the NBS solutions with the PV systems offers a genuinely holistic response to the intertwined challenges of climate change and energy poverty. While the PV addresses decarbonization and local renewable generation, the NBS simultaneously mitigate urban heat island effects. They also improve microclimate conditions in the area, enhance biodiversity, and strengthen social resilience. Together, they move beyond single sector interventions and create multifunctional public assets that generate energy, also reduce vulnerability, and improve quality of life. Public institutions such as schools, health centers, and social care facilities can act as anchor points for a socially inclusive energy transition. They are stable and trusted entities embedded in social local communities, often serving vulnerable groups. By integrating PV and NBS at these sites, municipalities or cities can then demonstrate tangible benefits, reduce operational costs on site, and channel savings toward social services and energy efficiency measures, while also creating visible examples for the climate action. However, pilot experiences clearly show that success depends on more than technical feasibility alone. Although technical potential such as roof capacity, grid availability, structural integrity, energy demand profiles are a key prerequisite, long-term viability is equally shaped by regulatory clarity, grid connection procedures, ownership structures, particularly permitting pathways, and other administrative steps. In many cases, these administrative processes, such as stakeholder alignment and institutional coordination, actually become more decisive than the engineering constraints. So therefore, scalable and replicable implementation requires not only sound technical design, but also regulatory readiness and infrastructural compatibility and strong local governance frameworks capable of managing this complexity. Only when all of these dimensions are addressed together can the coupled NBS PV solutions deliver a just and resilient, socially embedded energy transition. For the end, I would like to thank you all for your attention and really look forward to further collaboration in building resilient and inclusive energy communities across the Mediterranean.